Hello. This video is an introduction to the HC-SR04 sensor. This particular sensor uses ultrasonic frequencies to detect solid objects up to 4 meters away, although the best accuracy is achieved under 1 meter. This inexpensive sensor can be used in a variety of projects, including robotic vehicles, allowing them to avoid obstacles, or as a tool to accurately measure distance. One project which beginners can attempt to build is a distance sensor with audio-visual output, similar to parking assist systems found in cars. You should be able to make such project after watching this video if you have built some projects for Raspberry Pi with Python already. All you need is some LEDs, resistors, a buzzer, and the ultrasonic sensor. If you're up to it, you can also throw in a hush button to silence the buzzer. I will also show you in this video how to run Python code as a thread, which is essential when using this sensor. Let's start with the basics. This sensor is a 5-volt device, which means its output is not directly compatible with the Raspberry Pi, which can only tolerate 3.3-volt signals. However, you can use a simple voltage divider to step down the 5-volt signal and make the sensor work with the Pi. In a voltage divider, the resistors chosen are not as important as the resistance proportion. Here, the required ratio is 1 to 2. Following Ohm's law, the 5-volt supply voltage becomes exactly 3.3 volts at the reference point, and this is where the Raspberry Pi is connected to accept input from the sensor. I use 1 kilo ohm resistors to build my voltage divider. You can use what you have, but use at least 1 kilo ohm. Using resistors with resistance too low may actually draw too much current from the sensor and damage it. My divider is built using 3 resistors. Whenever 2 identical resistors are connected in parallel, their combined resistance is equal to their half, which equals to 500 ohms in my case. Here's the schematic diagram of the basic setup. The sensor has 4 pins, 5-volt power supply, ground, and 2 signal pins, trigger and echo. The voltage divider is only used with the echo pin. The trigger pin is connected directly to the Raspberry Pi, and the sensor will work fine with the 3.3-volt trigger signal. My go-to Python library for Raspberry Pi projects is GPIO0, which has a class called distance sensor designed for this particular sensor. This class has a number of useful features, including a basic event model, similar to how buttons work, where callback functions can be executed when objects enter and leave the sensor range. The default sensor range is set to 30 centimeters or about 12 inches, and this simple code can be used to turn something on and off, for example, a buzzer. More complex code to be run that way can be placed in functions. My button tutorial video provides a detailed explanation of the event-driven programming model. In another scenario, we can obtain a numerical readout from the sensor. By default, the distance sensor object provides the value as a floating point number up to 1 meter. A continuous readout can be implemented using an infinite polling loop. In this program, the sensor value is printed to the terminal 10 times a second. You can use standard Python formatting syntax if you want the sensor output to be more user-friendly. For example, you can round the sensor reading to a 1 centimeter accuracy. The sensor is more accurate than that, but certainly not down to 17 decimal points. If you have seen my other videos, you may be aware of my strong criticism against using infinite loops in programs. This is one rare case when such loop is actually needed. Unfortunately, such loops block the rest of the program, and it would be difficult for me to add any other components or code to this project and make it work. The answer to this dilemma is threading, which allows running pieces of a program concurrently. Using threading in Python is easier than you might think. You can run any chunk of code as a thread as long as it is a function. There are 2 steps required to convert this program to a threaded model. First, I need to move the loop into a function. Such change would not make a difference to the program yet, but it lays the foundation for the next step, which is introducing a thread. A thread is responsible for one function. Once started, it will run the function in the background. A thread is initialized with the target function name, which the thread will be responsible for. And by running it as a daemon, I don't have to do too much work once the thread task is complete. A thread does not start immediately, only after the start method is invoked. This updated program will perform as before, but now I can add code after the thread is started, which will now be executed. In fact, I actually need to add a pause statement, as the program would end right away without it. Pause was not needed before with the infinite loop non-threaded. Now that the infinite loop is no longer blocking the rest of the program, I could expand the project to my needs. There is one more thing to address, which is the loop syntax itself. Even when threaded, infinite loops are not necessarily a good idea, as they don't have a defined exit strategy. Depending what is happening inside of such loop and at which moment the thread stops, such loop may actually crash, resulting in unpredictable outcome after the program ends. A simple fix would be replacing the hard-coded true value with a variable which will be changed just before the program ends. Such approach will allow the loop to finish its iteration and allow the thread to shut itself down before the main program thread. If you are interested in displaying continuous sensor readout using an LCD display, please follow the video linked at the end. That's it! I hope this is a sufficient intro which will allow you to get started with this ultrasonic sensor. Just remember to run all infinite loops as threads. Thanks for watching.